And today, we're looking at something really innovative, I think. Harvesting energy from the vibrations in buildings and structures around us.
Exactly. Our source for this deep dive is a master's thesis by Danillo Gaspar at the University of Windsor. It's called Energy Harvesting for Slender Active Civil Foundations.
Sounds technical.
It is, but the core idea could give you one of those aha moments. Think about our bridges, our skyscrapers. What if they could actually be power sources?
Right. So the thesis is asking, can we capture energy from, say, a wind turbine swing by putting special piezoelectric plates inside the concrete?
Yeah, and how does that compare to other things like tiny MEMS devices? It's a really cool question. Let's unpack it.
Okay, so vibration harvesters. This is still an emerging tech, relatively speaking.
Right. The thesis explains them as ways to basically grab mechanical vibrations movement and turn it into electricity. It's part of that whole energy harvesting trend, scavenging power from the environment.
And there are a few different ways to do it, which the thesis outlines nicely. You've got piezoelectric ones first.
Okay.
These use materials where if you squeeze them or bend them, apply mechanical stress.
They generate a charge, like those novelty dance floors.
It's exactly like that. Yeah, same idea. Your footsteps provide the stress.
Got it. And then there are MEMS-based harvesters, micro-electromechanical systems.
Tiny little devices. The thesis mentions them for things like wearables, fitness trackers, maybe even medical implants.
Power just by you moving around. Imagine that, never charging your watch again.
It's a compelling idea. And there are also magnetoelectric harvesters mentioned.
Different physics involved there.
Yeah, they use the magnetoelectric effect. The thesis points to their use in, monitoring machinery health.
Yeah.
The machine's vibrations, power sensors that check if everything's okay.
It's amazing how much energy is just lost, isn't it? All around us.
It really is. And the thesis highlights the potential for powering wireless sensors in remote places.
Oh, right. Like environmental monitoring stations out in the middle of nowhere, no more battery changes.
Exactly, because the vibration energy is often continuous and it's renewable. As long as there's movement, there's a potential power source.
Okay, so that's the general concept. But this thesis gets really specific about putting these piezoelectric harvesters into concrete. Why concrete?
That's a key point. Concrete is everywhere in our infrastructure, but making it, it has a big environmental footprint.
Right. Cement production releases a lot of CO2.
A lot. So there's this big push to innovate to make concrete more sustainable, or even give it new functions, like energy harvesting.
And that leads to this shaping theory mentioned in the thesis, something about efficiency and potential failures.
Yeah, it's a way to figure out how well these embedded plates would work, and also to predict if the stresses they create might cause problems, like internal cracks reflecting stress back.
Okay, so the piezo materials stress them, they make electricity, embed them in concrete.
And if that concrete is part of a structure experiencing dynamic loads, cars on a bridge, wind on a turbine tower, those vibrations provide a stress.
Constantly generating little bits of power.
Potentially, yes. And the thesis compares this approach directly to using MEMS for energy harvesting in construction generally. They tested transducers at different frequencies too.
But it's not simple, right? The thesis mentions challenges. Concrete is stiff.
Very stiff. And that stiffness means vibrations tend to dissipate quickly through internal friction, damping. Less movement means less energy to harvest.
So how do you get around that? They talked about geometrically unstable piezoelectric ceramics. Sounds risky.
Well, unstable here is sort of the point, by design. The idea is that these special shapes might overcome the stiffness limitation by enabling resonant frequency synchronization.
Okay, frequency synchronization, explain that.
It's when the vibration frequency of the structure perfectly matches the natural inherent frequency of the piezoelectric element you've embedded.
Like pushing a kid on a swing at just the right moment.
Exactly, perfect analogy. When the frequencies match, the piezoelectric element vibrates much more strongly, generating significantly more electricity. It's way more efficient.
It's the sweet spot.
That's it. The thesis also mentions piezoelectric nanogenerators as another promising tech for this kind of mechanical energy conversion.
So, concrete, it's usually just seen as this inert structural mass, but this research reframes it.
It does. And the literature review in the thesis really hammers home the environmental side. CO2 emissions, massive resource use like sand and water.
Yeah, depletion of resources is a big one. And health issues from dust.
Respiratory problems, yeah. plus biodiversity loss from quarrying, even political and economic factors tied to the global industry. It's a complex picture.
So the drive for sustainable alternatives or improvements is really strong.
Absolutely. And that brings us back to things like wind turbine foundations.
Yeah.
Huge concrete structures, definitely experiencing dynamic loads.
Perfect candidates. And the really radical idea is actually making the cement itself piezoelectric.
Imagine that. Roads, bridges, building materials that actively generate power from traffic, from wind, from footsteps.
Wow. Okay, but this brings up resonance again, doesn't it? The thesis looks at analyzing structures like railway bridges with high-speed trains.
Yes, and resonance is tricky. It's a double-edged sword.
How so?
But when a structure hits its resonant frequency, the vibrations get much, much bigger. That's potentially great for energy harvesting, more vibration, more power. But those amplified vibrations can also dangerously stress the structure itself. Think of the Tacoma Narrows Bridge. Resonance can lead to failure.
Right, so it's a balancing act. Maximize energy capture without breaking the bridge.
Precisely. You need really careful material selection, careful placement of the harvesters. It's a complex engineering challenge.
And the thesis mentions that adding these systems creates a kind of structural dependency.
Yeah, you have to consider what happens if the harvesting part fails. Does it compromise the main structure? That risk needs careful evaluation.
Like tuning a guitar string, you said. Finding that resonant frequency is key.
It is. Matching the harvester's frequency to the structure's dominant vibration frequency is crucial for efficiency, but you have to do it safely.
The thesis also glances at other ideas from existing research, right? Like getting energy from asphalt.
Yeah, embedding piezoelectric symbols. That's the term used into roads to capture energy from traffic vibrations. Really interesting concept.
It sounds like something out of science fiction, but maybe not.
And it connects, conceptually at least, to regenerative braking in electric cars.
Ah, capturing the kinetic energy when you slow down.
Exactly. Converting that motion back into stored electrical energy. The thesis suggests that the control dynamics used in braking systems might even inform how we optimize vibration harvesting in structures. Real-time monitoring, adjusting energy conversion.
Smart systems.
Potentially, yes. Now, the thesis gets into some specific geometric designs they explored. This hexapole hyperbolic block lever system.
Okay, yeah. Sounds like a mouthful.
Yeah.
Hexagonal shape, triangular bits inside.
Right. And the specific design goal, according to the thesis, was to keep the internal angles quite small, less than 15 degrees.
Why that specific number?
It helps distribute the stresses compression, shear more evenly. It aims for more consistent von Mises stresses, which is a way engineers measure the overall stress state to predict material failure. It simplifies things, keeps the math more linear.
Okay, so the shape is about managing stress. And it relates to how things bend, flexure mechanics, and how they vibrate naturally modal analysis.
Exactly. They wanted to understand how this specific geometry affects the range of frequencies the system can harvest from the bandwidth. Analyzing the triangles helps understand the acoustic properties, the resonances.
And did they actually build and test this resonating coupling?
Yes, they did physical tests to see if arranging the triangles within the hexagon actually boosted the energy harvesting efficiency, trying to validate the theory.
The thesis goes into the math too, right? Vibration frequency, forces, damping.
Sets up the framework for analyzing the results. Concepts like vibration transmissibility, how much vibration gets through, and modal analysis for simple versus complex structures.
All building towards understanding resonance and frequency matching, especially for big things like turbine foundations.
Right. And they even estimate the potential energy available in things like railroad ties or wind turbine blades. It suggests there's a fair bit of energy there if we can capture it effectively.
And back to that 15-degree angle limit, it relates to a math simplification, the small angle approximation.
That's it. It keeps the linear equations used in vibration mechanics accurate. Go beyond that, and the math gets much trickier.
They also calculated moment of inertia for these shapes, how resistant they are to rotating.
Yes. Detailed tables for the hexagon and the block. And they introduced this concept of overlapped modal dynamic moments of inertia, considering its impact on design and harvesting.
So how did they actually test all this? What was the methodology?
They used dynamic testing, hitting the material samples and measuring the response. Hammer impacts were one method.
Just whacking it with a hammer.
A calibrated one, yes. They measured the input force and how quickly the vibrations died down, the energy dissipation. They also used the piezoelectric material itself as a sensor.
Clever. And they tried different things to harness sound energy too. A sliced block model.
Yeah, exploring ways to capture acoustic energy within the concrete. and they detailed the specs of the different piezo transducers they used.
It sounds thorough. Pendulum hammers, harmonic drives with eccentric loads.
Right, different ways to induce controlled vibrations, and an oscilloscope to actually see and measure the electrical output, the currents and loads generated.
They even mentioned the challenges of actually making the test blocks, 3D printing them.
Which is often a big part of experimental work. And alongside the physical tests, they ran computer simulations.
To model how the waves reflect inside, looking at eigenmodes and eigenfrequencies.
Exactly. The natural ways the structure likes to vibrate. They used Python for some bending simulations, fed in the material properties, set up detailed meshes for accuracy.
Okay, theory, methods. Let's get to the results. What did they actually find out?
Well, the hammer tests were interesting. They picked up the background 60 hertz electrical noise initially.
From the power grid.
Yeah, but the actual impact vibration dissipated very quickly within the block. And the frequency analysis showed more movement, higher displacement at higher frequencies.
And the tests with the controlled motor vibrations.
Those clearly linked the motor's input frequency to the voltage coming out of the piezo transducers.
Yeah.
That helped pinpoint the block's natural frequencies.
The frequencies where it resonates most easily?
Precisely. They also looked at density specifically, carving holes in the block. It made the block more flexible, allowing for larger displacement when it bent. Potentially better for harvesting, depending on the setup.
The simulations looked at different internal shapes too, right? Reflecting waves at different angles.
Yeah, 60, 120 degrees, etc. Analyzing displacement of the block's tips. The ANSYS simulations mostly lined up with other results, though there was one small anomaly.
And they generated some kind of graph to predict potential crack frequencies.
A dynamic phase transition graph, yeah. Could be useful for structural integrity analysis under load.
What about this complex field analysis using a Smith chart? That sounds advanced.
It is. It's a way to visualize the harmonic spectrum. They noted a conceptual link, not exact, but related, between a peak in their simulations around 430 hertz and the response of one transducer around 4 kilohertz.
Suggesting the models and reality were somewhat connected, even if the numbers weren't identical.
Right. It points towards maybe designing structures with specific resonant frequencies in mind to optimize energy harvesting. They also did a normal modes analysis confirming a range of natural frequencies.
Was there a standout result in terms of efficiency?
One key finding from the hammer simulation, really fast energy dissipation at 3.7 kilohertz when using a crystal that resonated at 6.5 kilohertz. It shows how critical that frequency matching, that resonance is for efficient energy transfer.
And they ranked the different piezo transducers they tested?
Yeah, they provided efficiency results for each. They also used an alpha chamber concept to test deformation under load.
And found
that larger ceramics with lower resonant frequencies seemed best for energy recovery in their tests. They also tied in some complex math lemniscate curves, more circled to understand stress impacts.
It sounds like finding that resonant point was the crucial thing, like tuning an antenna.
That's the analogy they used, and it really fits. Hitting that resonance makes the whole concept feasible.
Wow. Okay, so wrapping this up, this deep dive into Danillo Gaspar's thesis really does open up a pretty mind-bending possibility, doesn't it?
It really does. Turning our buildings, our infrastructure, into energy sources using these embedded materials and understanding vibration and resonance.
For anyone listening who loves those aha moments, this definitely feels like one. It points towards so much potential in material science, structural engineering, sustainable energy.
It gets a lot of different fields.
So here's the final thought for you, the listener, to chew on. Could our future cities actually draw power from the concrete and steel surrounding us? From the roads we drive on?
And what other parts of our environment, things we think of as totally passive, might actually hold untapped energy potential? It makes you wonder. We definitely encourage you to think about these implications, maybe look more into piezoelectricity, vibration harvesting, sustainable building. It's a fascinating area.